Hello students, welcome. Today Form 4, we are going to introduce topic 3. The name of the topic is known as Chemistry of Reaction Rates and Reversible Reactions. We are going to start lesson 1. So what is reaction rate? Reaction rate is the measure of how much of reactants are consumed or are used, or how much of the products are formed or are produced by unit time. Next, chemical reactions proceed at different speeds. There are some reactions that proceed at a high speed, some they proceed at a moderate speed, while others proceed at a low speed. So we are told some reactions take short time to occur, that means at a high speed, while others take longer, that means some others take at a slow speed or a slow rate. Example, we are told barium sulfate is precipitated immediately. Solutions of sodium sulfate and barium nitrate are mixed. So in other words, precipitation reactions takes place at a higher speed. Okay, next we are told while rusting of iron takes place at a very slow speed. That means rusting of iron takes or proceeds at a slow speed. Okay, even we have some reactions which takes place at a moderate speed. A good example is the reaction between zinc and dilute sulfuric acid or dilute hydrochloric acid. So next, we are going to go to quantities measured and used to determine reaction rates. 1, the volume of gas produced by unit time. 2, loss of mass by unit time. Number 3, the formation of a precipitate by unit time. Number 4, the change in color intensity by unit time. Then next, we are told when reactants combine to form products, the amount of reactants decrease as that of the products increases. So we have a small curve here. Here we are having a curve for products, and this is the curve for reactants. We have time in our x-axis, then we have concentration, which is measured in moles per decimeter cube on our y-axis. So here we are told when reactants combine to form products, the amount of reactants decrease. You see, this is reactant side. The amount of reactants or the concentration of the reactants is decreasing as time goes. And we are told as that of the product increases. As you check, we are having the product which increases as time goes, like that. So we are told when reactants combine to form products, the amount of reactants decrease as that of the products increases. Okay, next we are going to go to the collusion theory and also activation energy. So we start. What does collusion theory states? It states that for a reaction to occur, reacting particles must collide with their correct orientation and must have a certain minimum energy known as activation energy. Activation energy is written EA. Okay, we are told not all collusions results in a chemical reaction, but only successful or effective collusion or fruitful collusion results in a chemical reactions. So when you are stating the collusion theory, you are supposed to capture 3 things. That 1, the reacting particles must collide. That's 1, and they have to collide within their correct orientation, and they have to have that minimum energy known as activation energy. So we are told not all collusion result in a chemical reaction, but only successful collusion or effective collusion or fruitful collusion bring about chemical reaction. We are told note, the higher the number of successful collusion or effective collusion, the faster the rate of the reaction. That one we are going to see when we are dealing with the factors affecting the rate of a reaction. So next, we are going to go to activation energy. So what is activation energy? Activation energy is the minimum amount of energy required for the reacting particles to cause successful or effective collusion to form products. Okay, it refers to the energy barrier that must be overcome by the reactants to be converted to products. So if there is no activation energy, that means those reactants can never be converted into products. So this energy barrier determines the magnitude of the activation energy of the reactants. Activation energy on energy level diagram for an exothermic reaction. So here we have energy which is measured in kilojoules per mole, and here we have reaction path. This is an energy level diagram. We can as well write there reaction progress or reaction coordinates. So here we have reactants, because we are dealing with exothermic reaction here, and in exothermic reaction we said the reactants are having higher energy content than the product. So this is our activation energy. Here is our activation energy. So these are reactants and these are our products. So the enthalpy change here will be negative, because enthalpy change or heat change is gotten by enthalpy of product minus enthalpy of reactants. Okay, the activation energy is there. You have to know that. Then when we are dealing with that activation energy on energy level diagram for an endothermic reaction, remember we said in an endothermic reaction, the reactants and the products are having a higher energy content compared to the reactants. That's why we are putting the reactants up there and we are putting the reactants down here. So the activation energy is here now. So the activation energy is larger or longer when you compare with that side of an exothermic reaction. Okay, here is where we are going to have our enthalpy change, which is positive, because endothermic reaction results in a positive enthalpy, because the products are in a higher energy content compared to the reactants. So that's the end of our lesson.